So page table entry now have a present bit for to use the swap space as a extension of the main memory. And page 4 is raised by architecture when the target page's present bit is off. Then what? Page 4 handler will be invoked to resolve this page 4 situation. So it's a kind of a problematic situation because processor is to access the memory, but the corresponding data is not present in the main memory. main memory 하니까 되게 헷갈려요. Physical memory. So this is a problematic situation, and the operating system needs to resolve this one. By how? By bring the stored stashed data onto the main memory again. Okay, so page 4 handler is taking in that responsibility. And if there is a free slot, there is an unused frame in a main memory, things are pretty simple. Just to find out the location of the swap, the location of the page contents in a swapping spaces, and then copy those data to a free frame and update the page table. Then things resolved, and then restart the instruction. And restart of the instruction is easy. Just after treating them, just complete the interrupt handler. Then what? To the computer architecture's perspective, the program counter remain at the same instruction, so it will repeat executing the same instruction. And now the page content is placed on a physical memory, so page 4 will not happen in second turn. Good job. So things will be resolved. But more common case is that, yeah, we need to bring the stashed data to the main memory, but there is no free frame available. All frames are in use. Then what? We need to pick one of a frame, one of the pages, and swap that page out and preempt that frame and bring the needed data to the physical memory. Page 4 handler needs to do that. Yeah, do that job. Okay, so the location of the page in a swap space will be stored in a page table or some other place in a kernel data structure. And since it involves some communication between the main memory and IO devices, typically hardware device or hard disk driver kind of stuff, it'll take a relatively large, long time when it compared to the ordinary memory access. So process will be temporarily blocked for this IO operation in many cases, because in order to give a chance for other process to use a CPU in meantime. Okay. Yeah, so page fault and consequent page in and page out operations are all taken place transparently to the process. What it means here. For user program's perspective, it have no idea at which moment page 4 is raised and at which moment which pages is actually placed on physical memory or swap space, and at which moment things are exchanging between two devices. Those informations are not visible to the user's program perspective. 그렇겠죠? And user program do not need to do anything regarding this type of management stuffs. But just use a computer upon the nice abstraction on virtual memory. 그렇죠? User program does not need to be involved in anything on these management operation. In that sense, all these operations are transparent to the process. Because things happen seamlessly. The only possible way to user program to experience this operation is time delay between two instructions. Suddenly, maybe suddenly between two memory accesses, the access time suddenly, the cost for memory access suddenly increase at some point if it involves page faults and stashing and different IO operation. But except for the time performance, in terms of the functionalities, things are all happen seamlessly. Okay, so page fault control flow algorithm. So this is the algorithm of the computer architecture. So note that this one does not work as in a sequential manner. This is only a description of hardware functionality. So everything are pretty the same as for we have for TLB mechanism and page mechanism and so forth. The only addition is that, yeah, we have another else if case that check whether physical table entry, the present bit is true or false, and if it is false, what? It raises exception of the page fault handler. So this is the only change in computer architecture side. And all complicated stuffs are dedicated, are given to the operating systems part, which is a page. Complicated stuff is taken charge by page fault, and the key of the page fault handler is page replacement. So page faults usually happen when memories are busy, because only when memories are busy, things are swapped out and pages are placed on a subspace, and then it is read requested to be loaded to the memory. In such a cases, to bring the swapped out data back to the memory, we need to replace the pages. Replace the one in the sub memory and the one in main memory. So before, what this is, before what? I think this is a broken sentence. Before accessing a page, I guess, before accessing a page, OS must page out, sorry, this is right, sorry. Before page in, I use page in here as a verb to refer an action that bring the swap page back to the main memory. I call that action just the page in. So before paging in our page, the page fault handler must select one of the page that is placed in a physical memory and page out that page to make some free spaces. Right. Yeah, and such page out action should happen when memory is almost fully used. I mean, if memory is not that busy, we don't need to really swap out anything. Just allocate a new data, allocate a free available frame to a new pages. But if a memory is almost busy, pretty busy, then we need to swap out the data. But usually this swapping out operation does not only happen when page memory is full, but also it happens when memory is likely full. So it's not, even if it is not 100% full, if a memory is like 80% full, then operating system proactively page out the existing pages to the swap spaces. Why? 왜 그렇게 할까요? Why? Operating system proactively works to page out. Because when things happen, I mean, if a swapping try to happen, then in a near future, more swapping will be demanded as well. 한번 이게 페이지, 이렇게 스와핑이 일어나기 시작하면은 좀 있으면 더 많이 일어날 수도 있다. So in order to save a time for future need, it proactively works to start to page out some unused, not frequently used pages to the swap space to hold some available memory so that system can quickly respond to pay the new need for paging in the old data. So most OS have a high and low watermarks for page demand. So system usually run a page demand. You can think of it as a kind of a small thread inside of the kernel. that monitor the use of the memory, and if the use of the memory exceeds some boundary, then what? This daemon starts to do the page out, so that makes some room in the main memory. So it happened in a background. So it casually happens. So usually system have a high watermark and low watermark. There's a watermarks in a memory management system. So if a system reaches the low watermark, low watermark means, so watermark here indicate the amount of the free memory in physical memory devices. And if it hits low watermark, then it's almost out of a free spaces, so that the system may not immediately serve a new request of the memory. Then what? Page daemons start to page out to occupy a free available space up to the moment it reaches high watermark. 그래서 예를 들어서 low watermark might be 10% of the main memory. So if it reaches to the 9%, then daemons start to page out some less important pages in a memory for like, if the high watermark is a 20% point, then until the system occupy of 20% of the free memory. So system behave proactively responds to preparing some free memory in the main memory spaces. And 생각해 보세요. Yeah. And then also, and here anyway, the swapping or page replacement is happen when computer starts to load many programs at the same time. Then OS must make a proper page replacement policy for deciding which page is to be swapped out and which page is swapped in, because page in and page out operation incurs a lot of the runtime cost. So usually disk access takes what, 10,000 or 100,000 times longer than a single memory access. 그쵸? So if a wrong decision is made, so that if we swap out some important pages, then for example, TLB is a cache to the page table, right? So TLB also needs to have a replacement policies, but we don't discuss that issue when we learn TLB, because the same policy works consistently to the TLB as well. 예. 그래서 여기서 이런 replacement policy에 대해서 이제 이야기를 할 겁니다.